function f of x be piecewise continuous on interval from 0 to L. Then there are three distinct ways how we can expand function to interval from negative L to L. So I'm going to draw three different ways how we can expand the function. The first one, if we have a function and say function looks something like that, and L is somewhere here, then we can expand it to the interval from negative L to 0 by pretending that our function is even. I'm going to get a piece which looks like this. Even. Or we can pretend that our function is odd. Then extension is going to look like this. Or we can pretend that from 0 to L and function will start repeating itself afterwards. 12, 3L, negative L. We have three distinct possibilities: even expansion to interval from negative L to L, odd expansion, or we can pretend that from 0 to L the function is the whole period. Okay. Now if you want to find the Fourier series in each case, for the first case we're going to get the Fourier cosine series. So we're going to get f even, which equals to a0/2 plus sum, and from 1 to infinity, an cosine of pi n x over L, where an equals to 2 over L integral from 0 to L f of x cosine pi n x over L dx. In the second case, we're going to get the Fourier Sine series. So we will say f odd equals sum, and from 1 to infinity, bn sine of pi n x over L, where bn equals 2 over L integral 0 to L f of x sine of pi n x over L dx. In the third case, we're going to get just the Fourier series. Notice that we're going to have argument of sine and cosine. When we're going to be writing them, we're going to have pi n x over, and we're supposed to divide by half of a period, and because our function has period from 0 to L, so the length of the whole period is L, so half of that period is going to be, so from negative L to L, it's going to be doing period twice, so we're going to divide by L over 2. So we're going to get 2 pi n x over L. So our Fourier series in this case, f tilde of x is going to be equal to a0 over 2 plus sum n from 1 to infinity and cosine of 2 pi n x over L plus bn sine of 2 pi n x over L, where an equals 1 over L, integral from 0 to L. So we divide it by 1 over L, because from 0 to L we have a whole period. So function f of x cosine of 2 pi n x over L dx, and bn equals to 1 over L, integral 0 to L, f of x sine of 2 pi n x over L dx. We have function f of x which equals to x squared on interval from 0 to L. We want to find its Fourier cosine, Fourier sine, and Fourier series. So we start the fact. So first thing we'll do, we'll calculate a0. a0 equals 2 over L, integral 0 to L, x squared dx. To find a0, we need to find integral 0 from 0 to L x squared dx, because that's our function, and you multiply by 2 over L. So we're going to get 2 over L x cubed over 3 from 0 to L. So we're going to get 2 over L cubed over 3. So we're going to get 2L squared over 3. That is our a0. To find an, we need to calculate integral x squared cosine x dx. So we do integration by parts. U equals to x squared, v prime equals to cosine x, v equals to sine x, u prime equals to 2x. So we're going to get uv x squared sine x minus integral 2x times sine x dx. So it equals x squared sine x minus. For this part, we'll do integration by parts one more time. U equals to 2x, u prime equals to 2, v prime equals to sine x, v equals to negative cosine x. uv negative 2x cosine x minus 2 times negative cosine x dx. So we're going to get x squared sine x plus 2x cosine x, minus minus give us plus, extra minus another minus, antiderivative of cosine is sine, plus c. Okay, now we're going to use it to calculate an. So expression for an is going to be an equals 2 over L integral 0 to L f of x cosine of pi n x over L dx. In our case, f of x is x squared cosine of pi n x over L dx. We're going to be doing W substitution. So W equals pi n x over L. So x equals L W over pi n, and dx equals L over pi n dw. x is changing from 0 to L, so W will be changing from 0. When x equals to L, we're going to get pi n. So we got new integral 2 over L, integral W equals to 0, W equals to pi n. X squared will be L W over pi n squared cosine of W, and dx will be L dW over pi n. That expression equals to, I'm going to take 2 over L integral 0 to pi n L squared W squared pi squared n squared cosine of W L dW pi n. So it equals, I'm going to take all the constant outside, 2 over L squared pi squared n squared L pi over L over pi n. And we're going to left integral 0 to pi n W squared cosine of W dW. L and L will be cancelled out, so we have 2L squared, and we have pi cube and n cube on the bottom. We already calculated that integral W squared cosine of W just a second ago. It was equal to W squared sine of W plus 2W cosine of W minus 2 sine of W, and we're doing it W equals to 0, W equals to pi n. So we're going to end up with 2L squared pi cube n cube on the bottom. Sine of pi n equals to 0, sine of pi n equals to 0. So when we substitute in pi n, we're going to get 2 pi n cosine of pi n. And when we substitute in 0, 0, 0, and 0. So that's all what are left. So we're going to get 2 times 2 is 4, L squared. We're going to reduce pi and pi cube, so we have pi squared left, and n cube, so we have n squared left. And instead of writing cosine of pi n, we're going to write down negative 1 to n. So finally, we get expression for n equals to 4 L squared times negative 1 to n over pi squared and n squared. That is when n equals to 1, 2, and so on. And you recall that a0 was equal to 2L squared over 3. So we are ready to give our answer to part A. So cosine expansion for the Fourier cosine series f even is going to be equals to L squared over 3, a0 over 2, plus, and from 1 to infinity, 4 L squared over pi squared n squared times negative 1 to n cosine of pi n x over L. So that will be answer for part A. To do part B, to find the Fourier sine series of function, we need to find Bn, and preliminary we'll calculate integral of x squared sine x dx. That is going to be again integration by parts twice, so we're going to get negative x squared cosine x plus 2 integral x cosine x dx. So we're going to get negative x squared cosine x plus 2 cosine x plus 2x sine x. Now to find Bn, Bn equals 2 over L integral 0 to L x squared sine of pi and x over L dx. We'll do substitution. We already did it in the verb part A. W equals to pi and x over L. So x equals to LW over pi n. So dx equals to L over pi n dx. X is changing from 0 to L. So W will be changing from 0 to pi n. So we proceed with substitution. We're going to get 2 over L integral 0 to pi n L W over pi n squared sine of W L over pi n dx. So we're going to get 2L squared over pi n cube integral from 0 to pi n W squared sine of W dW. So we're going to get 2L squared over pi n cube. And we already know integral, value of integral, so it's going to be negative W squared cosine of W plus 2 cosine of W plus 2W sine of W. And we calculate that expression from 0 to pi n. So we're going to get 2L squared over pi n cube. So when substituting pi n, we're going to get negative pi n squared cosine of pi n plus 2 cosine of pi n. Sine of pi n equals to 0. Now if substituting 0, we're going to go to that minus 0, 0, and cosine of 0 is 1, so minus 2. So I'm going to distribute multiplication, so we're going to get 2L squared over pi n cube times negative pi n squared cosine of pi n. So pi n cube and pi n squared will be reduced, plus 2L squared over pi n cube times 2 cosine of pi n minus 2. So we're going to reduce that expression into 2L squared over pi n. Cosine of pi n we're going to write as negative 1 to n plus extra minus, so negative 1 to n plus 1 plus, we can take 2 out from that expression, so we get 4L squared pi n cube negative 1 to n minus 1. That is our expression for Bn. when n equals 2, 1, 2, and so on. Now that we know what Bn equals to, we can write down the Fourier Sine series for function f of x. So f hat equals to sum and from 1 to infinity Bn, which is 2l squared negative 1 to n plus 1 over pi n plus 4l squared times negative 1 to n minus 1 over pi n cubed times sine of pi n x over L. That is our answer for part B. That is the Fourier Sine series of function f of x. Now to do part C, we need to find a0. So a0 is going to be 2 over L integral 0 to L x squared dx. So it's going to be equal to 2 over L x cubed over 3. So it's going to be 2L squared over 3. We also need to calculate n. So it's going to be 2 over L integral 0 to L x squared cosine of now we want to be careful a little bit because the whole period of function equals to L. So we're going to write down pi and x on top, but on the bottom you have to write down half of a period of function, and the half of a period of function in this case is going to be L over 2 dx. So we're going to get 2 over L integral 0 to L x squared cosine of 2 pi n x over L dx. And calculations will be similar to what we already did in part A. So that is going to be equal to L squared over n squared times pi squared. Formula for Bn is similar to formula for An. The only difference, instead of cosine, we're going to write down sine. So we're going to get 2 over L integral 0 to L x squared sine of 2 pi n x dx, and that's going to be equal to negative L squared over pi n. And now we are ready to write down what will be tilde function for a series. So it's going to be a0 over 2 L squared over 3 plus sum, and from 1 to infinity an, which is L squared over pi squared and n squared cosine of 2 pi n x over L. My previous calculation, I forgot to put L here in the sign. Minus L squared over pi n sine of 2 pi n x over L. And that's how answer for part C is going to look like.